Next up, we have Nate Diamant. Nate is a machine learning researcher on the research biology AI ML team at Genentech Early Research and Development, GRED, where he works on representation learning and graph neural networks. Nate was previously at the Broad Institute, working on representation learning of cardiovascular data, and he'll be talking about deep fitness inference for drug discovery with directed evolution today.
Yeah, thanks for the introduction. Okay, let me get to my screen again. There we go. Okay, great. Yeah, so I guess we already got my first slide. So first, just a quick overview of what directed evolution is and why it's interesting. So directed evolution is an experiment run in the real world, in the lab, for optimizing genotypes towards a specific goal. So our goal at Genentech is going to be drug discovery. Directed evolution is so powerful because it can search combinatorial genotype space with 10 trillion genotypes tested in parallel in every round. So directed evolution, in the most abstract sense, consists of this loop here, which is you test the genotype's effectiveness, then you remove the worst genotypes in some way, and then you upsample and mutate the surviving genotypes after the removing step. Now, compared to a computer, directed evolution can test 10 trillion genotypes at once, so it's much faster. But also compared to a computer, it's not doing simulation. It's directly testing the genotypes against your goal. So it's also more accurate, faster and more accurate than a computer. And as for significance, in 2018, the Nobel Prize in chemistry went to people who developed technology for directed evolution. So what does the data look like from a directed evolution experiment? So basically every selection round, that loop we looked at in the last slide, you take a subsample of the genotypes that survived the removal step. And what that gives you is a table where you have genotypes for rows. And then each column is a different round of selection. And you have a count for how many times you sampled that genotype from the population. So our goal is going to be to use that data to infer which is the best genotype, or what are the best genotypes, because we'll try to select a lot of them. The most simple way to do it is to just take the genotypes that have the highest count in the last round. So that would be this blue box in this example data. And it turns out that this is what many biologists and chemists do, basically just relying on the strength of the directed evolution experiment. However, sometimes good genotypes can mutate in late and don't have much time to increase their population. For example, this green square, where it mutated in on round 2 and then increased a lot in the final round. So we will use a model called fitness from population genetics to pick these rising stars that might be missed otherwise. And just a quick note is that prior work has also looked at this data and has focused just on the last round or last 2 rounds. Okay, so what is this fitness model? We'll start by defining fitness, which we call W, in a very simple way, where fitness is just the number of children. Fitness is just the number of children you have, or a genotype has, from one round to the next. Now, we can rearrange this equation in order to write fitness in terms of population frequencies rather than total counts, because our data only is a subsample of the total population. Basically, what this new equation says is that genotype fitness, if it's above the average fitness, then its frequency will increase in the next round, and vice versa. So this is the fitness equation. Our goal is going to be to use this fitness equation to infer fitness from our time series count data. We'll fit W using gradient descent to maximize the log likelihood of the data. So the most simple way to model the count data is to just use a multinomial distribution where the multinomial frequency is determined by the fitness equation. However, the multinomial distribution does not take into account the fact that we might want to make less confident predictions when we have fewer data in the prior round, when we have fewer total counts. So instead of using the multinomial distribution, we can use the Dirichlet multinomial distribution, which allows us to scale our confidence by the total count in the prior round. Dirichlet multinomial is like a multinomial, but over dispersed. Okay, so this gave us two ways to model the likelihood of our data in terms of fitness. Now onto what deep fitness is. So in the prior slide, we focused on having one fitness value, one like W per genotype, but that has a couple limitations. For one, what if we want to make predictions on genotypes that we didn't see in the training data? And another limit is that we might want to account for the fact that similar genotypes should have a similar fitness value. The way we'll do that is we'll train a neural network to predict fitness from genotype. This neural network can be, again, just trained using the maximum likelihood approach to maximize the likelihood of the data. And in our case, we used a transformer, which are kind of the best sequence models now. So we have defined a couple of fitness models, a per genotype fitness model and a deep fitness model. So how do we evaluate them? The way we evaluated in our current work is to look at enrichment prediction. So enrichment is just the ratio of the population frequency of a genotype, but divided by its frequency in the prior round. We did two types of holdout evaluations to see how well we predicted enrichment. The first one is holdout round generalization here on the left. So basically train on the first T-1 rounds and then predict enrichment in the final round T. And this is sort of asking, can we predict the future of the experiment? The second holdout was to hold out both the final round and hold out some genotypes. And this is where we can really see the advantage of deep fitness, because only the deep fitness model can make predictions on unseen genotypes. So now onto some results looking at the Pearson R of predicting the enrichment on those holdouts. So first, some simple baselines. The most important baseline to look at right now is the prior round enrichment, which is basically saying, look at the enrichment in round T-1 and just assume it stays the same for round T. And this is actually not a terrible model. Now onto the per genotype results. So what we can see here is these per genotype models get a pretty significant bump over just using the prior round enrichment. So this is important to look at for biologists and chemists who may also know about the enrichment-based approach, but our approach using fitness allows us to take into account all of the rounds, not just the second to last round. And it also looks like using the Dirichlet multinomial improves results over the multinomial. And finally, on to deep fitness. So deep fitness, the multinomial performed surprisingly badly, maybe due to some overfitting. But the deep fitness with Dirichlet multinomial performed about as well as just having a per genotype on the data on the genotypes that had been seen during training. But it also has this excellent advantage of being able to make predictions on unseen genotypes, and it generalizes very well to unseen genotypes. So, okay, on to another evaluation, more qualitative. We also tried to evaluate the diversity of the top genotypes selected according to our fitness model. So first, we trained a variational autoencoder just in the genotype sequence space to try to visualize the sequence space. Then we mapped that, then we visualized that using UMAP. And then on the left here, we plot the top 50 genotypes according to last round frequency. And those are shown in the green dots on top of the space. And then on the right here, we mapped the top 50 according to the fitness model. And as you can see qualitatively, these green dots in the fitness approach are much more spread across the genotype space. So not only does fitness provide better predictions of enrichment, but it also seems to lead to more diverse hit selections, which is important for target finding. So overall, in conclusion, direct evolution is an incredibly powerful type of experiment, but you don't want to just read winners off from the last round. You also want to take into account the data from all of the previous selection rounds. Deep fitness performs better, or at least similar to per genotype fitness, but can also make predictions on new genotypes due to being parameterized by a neural network mapping from genotype to fitness. And then finally, fitness modeling can help improve hit diversity. Okay, with that, I just wanted to give a quick overview of our of the department I'm in. Here's what we work on: graphs and sequences, computer vision, and biology, lots of areas. So if anyone's interested, please reach out. And then finally, I would just like to acknowledge my co-authors, in particularly Gabriele and Max Shen, who helped formulate the whole project. Thanks.
Great. Thanks, Nate. Excuse me, for the excellent talk. Again, folks, if you have any questions, feel free. We have a couple of minutes or so. But in the interim, did you happen to run any ablation tests on looking at the relative depth of the neural network?
On the depth of the neural network, we didn't explore the architecture too much. I'd say we got pretty good results quickly with a relatively low parameter neural network. Maybe with like a larger scale data set, the scaling would start to matter more.
Got it. All right.
Do we have a minute for a follow-up question? If
We
don't
do.
have...
We most certainly do. Yeah.
I was curious. Thank you for the talk. That I really appreciated. I was wondering, how would you do you think the metrics? I was kind of curious about why the metrics bumps from 0.40 to 0.45. It's a bit of a technical question on those whole genotypes. So I was just wondering, because you did this work on applying an autoencoder and having some kind of representation of those genotypes anyway, did you try holding out genotypes that are very diverse and trying to see if these numbers get down by a lot when you transfer to very different phenotypes? Because when you deploy those type of models in real world, like, and if you want these models at the end to be able to spit out results for unseen genotypes and select genotypes in the future, you do need to check performance across slightly different sequences somehow.
Yeah, that's an excellent question. We didn't really do like a split on having extremely different genotypes. I think that'd be especially important as we start to think about optimizing the sequences like not in the experiment, like using a latent space type optimizations, because in those cases you can get out of your data distribution pretty quickly. So yeah, that's a really important thing for continuing the work, I think.
Okay, thank you.
Thanks for the question, Ramon. All right, and thank you again, Nate, for the wonderful talk.
Thank you.